Principle number 2 then says that when you have bonding and anti-bonding molecular orbitals, that's because the two atomic orbitals create two molecular orbitals, all right? And one of them is lower in energy, it's the bonding molecular orbital, and the anti-bonding molecular orbital is higher in energy. That does not make the molecule stronger. The third principle just says that as you start applying electrons to these molecular orbitals, you always start at the lowest molecular orbitals and work your way up to the highest molecular orbitals. And in chapter 3, we talked about Pauli exclusion principle, how every electron needs its own set of quantum numbers. In this world, Pauli exclusion just means every electron has to be different from the other electrons, and we'll talk about that. Hund's rule is the rule that said that each electron gets its own orbital first, and you only pair up when there's no more room left to do anything else. And we'll see examples of both of this as we go through and we assign electrons.
In contrast to valence bond theory, which assigns bonding orbitals to individual atoms, molecular orbital theory assigns the orbitals involved in bonding to the entire molecule. The simplest illustration of molecular orbital theory can be seen with the hydrogen molecule. According to molecular orbital theory, the 1s atomic orbitals of the two hydrogen atoms combine to give two molecular orbitals. Because atomic orbitals are wave functions, they can combine either constructively or destructively. Additive or constructive combination of the two atomic orbitals gives a bonding molecular orbital, while subtractive or destructive combination of the two atomic orbitals gives an anti-bonding molecular orbital. The bonding and anti-bonding molecular orbitals formed by the combination of two 1s orbitals are called sigma 1s and sigma star 1s respectively. The bonding molecular orbital, sigma 1s, is lower in energy than the original atomic orbitals. And the anti-bonding molecular orbital, sigma star 1s, is higher in energy than the original atomic orbitals. Like atomic orbitals, molecular orbitals can accommodate a maximum of 2 electrons each, with the electrons in the ground state occupying the lowest possible energy orbitals. The molecular orbitals in the hydrogen molecule can be represented with lines or boxes placed at the appropriate relative energy levels. The 2 electrons in the hydrogen molecule both occupy the bonding molecular orbital. Because most of the sigma 1s bonding molecular orbital is located between the 2 nuclei, electrons in this orbital draw the 2 nuclei together by electrostatic attraction. The sigma star 1s anti-bonding molecular orbital consists of 2 lobes. The majority of the space occupied by the 2 lobes does not lie between the 2 nuclei. In this molecular orbital, the region between the 2 lobes is known as a node. Electrons in this orbital would actually draw the 2 nuclei apart by electrostatic forces. Hydrogen has no electrons in this anti-bonding molecular orbital.
Okay, a lot of information in that video, but that's a great overview of how to build the H2 molecular orbital. So let's try and break that down a little bit and see what's happening. So at the beginning of the program there, it showed the atomic orbitals of hydrogen. And again, on the far left and the far right, that's where the hydrogen atomic orbitals are. So this is a hydrogen atom on the far left, and this is a hydrogen atom on the far right. And initially, they each have a single electron because they're 1s1, okay? And when you make a molecular orbital then, 2 atomic orbitals in make 2 molecular orbitals. The lower orbital is the bonding molecular orbital, and they call it sigma 1s because it came from 1s orbitals. But the lower bonding has to be countered by a higher anti-bonding molecular orbital, and that's called the sigma star 1s, and that destabilizes the molecule. There's actually no electrons between the nuclei, so that's going to basically break the bond. So that's building the molecular orbital diagram. And now to assign electrons, you have a total of 2 electrons to assign, one from the first hydrogen and one from the second hydrogen. And you literally just start putting them in the lowest molecular orbitals first and go up. So in this case, the 2 electrons both go to the sigma 1s molecular orbital. And you can see how one is spin up and one is spin down, so they each have their own quantum signature, which is Pauli exclusion principle. And there's no electrons in the antibonding sigma star 1s molecular orbital. So this is the molecular orbital diagram for H2. And you can probably see that there's going to be more electrons in the bonding than the anti-bonding. So that makes it a more stable version than the individual hydrogen atoms that come together. We'll talk about that in a little bit. But if nothing else, remember earlier I talked about how there are have no fear of ice clear brew, the 7 diatomics. Hydrogen is one of them. And that's why hydrogen is almost always H2 and not just H, because there's an energy savings, if you will, making the H2 molecule relative to the H atoms. Now, for dihelium, you would have a helium atom on the left and a helium atom on the right. They both have one atomic orbital, so we're going to make 2 molecular orbitals then. One will be lower, that's the sigma 1s orbital. That doesn't show it in the picture, but that's the sigma 1s there on the bottom. And the sigma star 1s, the anti-bonding molecular orbital, is on the top. Now, the difference between helium and hydrogen, helium has 2 electrons. So on the first helium atom, you could draw 2 electrons for that one. And on the second one, you could draw 2 electrons for that one. So we have a total of 4 electrons to place in the molecule. And like before, we'll put them in the lower orbital first, the bonding molecular orbital, and then we'll put any left over in the anti-bonding. And as you can see, since we have 4 electrons, the first 2 go in the bonding sigma 1s, but there's also 2 electrons in the sigma star 1s. So dihelium has just as many bonding as anti-bonding molecular orbital electrons. And we're going to see that makes the molecular orbital for He2, dihelium, not very attractive energetically. Instead of just thinking about maybe it's good or not good, let's talk about a way to quantify if you make a molecule or not. And scientists do this with what's called bond order. And for molecular orbital theory, bond order equals 1/2 parentheses the number of bonding electrons minus the number of anti-bonding electrons. If you have a bond order that's greater than 0, that means that it's a stable molecule, and that molecule should exist. However, if you have a bond order of 0, and in higher applications you might see even a bond order that's less than 0, but we're not going to talk about those all mean that you have unstable molecules, and the molecule should not exist, all right? So bond order, if it's greater than 0, that means it's going to happen, it's going to exist. So in dihydrogen, if you remember, we had 2 sigma 1s electrons and no sigma star 1s electrons. So bond order for that, 1/2 parentheses bonding minus anti-bonding. This would be 1/2 parentheses 2, because there's 2 electrons there, minus 0, because there's no electrons there. 1/2 parentheses 2 minus 0 parentheses 1/2 of 2, bond order 1. This is a stable molecule, and you bet H2 exists. Most hydrogen exists as diatomic hydrogen. It's rare to have hydrogen atoms unless you're like on the surface of the sun or in a lab or something like that. Now, dihelium had a different molecular orbital diagram. It had 2 electrons in the sigma 1s and 2 electrons in the sigma star 1s. So notice it has just as many bonding as anti-bonding electrons. Well, you can do a bond order analysis for this as well as for hydrogen. And again, if that bond order is greater than 0, the molecule exists, but if it's equal to 0 or less than 0, it's not going to happen. So in dihelium, bond order equals 1/2 parentheses bonding minus anti-bonding parentheses. So in this case, that's 1/2 parentheses 2 minus 2, 1/2 of 0 equals 0. That's unstable, and we would not predict the dihelium molecule to exist. And I don't believe that dihelium has ever been made. There's no reason for it to be made energetically. There's no energy savings, if you will, having that happen. So dihelium does not exist. So bond order will be really useful to us as we figure out how these things go. Now, in the Lewis structure, there's an equivalent idea for bond order. And I have up here just a molecule, acrylonitrile, trial. And I like this molecule as an example because you can probably see there are single bonds, there are double bonds, and there are triple bonds. And so in a Lewis structure, if you have a single bond, that's a bond order 1. So if we calculate a bond order of 1 in molecular orbital theory, that corresponds to a bond order of 1, a single bond in Lewis structures. And likewise, in a Lewis structure, a double bond would be bond order 2, and a triple bond would be bond order 3. And this can be pretty important. We're going to see that as bond order goes up, your bond length goes down. So the bond order 2 double bonds are shorter, tighter together than bond order 1 single bonds. And triple bonds are even shorter than double bonds. And molecular orbital theory has all these same kind of things. So a bigger bond order means tighter, smaller bond length and stuff. It's pretty cool. We'll talk more about this as we go through the class, but that's the equivalent idea of a bond order in a Lewis structure versus molecular orbital theory, which is what we're doing right now. This is a question you might see. What is the carbon-oxygen bond order in formaldehyde? Formaldehyde is CH2O, the structure's there on the right, and we want to know what the bond order is between the carbon and the oxygen. Well, you can see in that Lewis structure that between the carbon and the oxygen, there's 2 lines. That's 2 bonds, a double bond. And bond order of 2 is what a double bond means. So every time we see a bond order 2 in molecular orbital theory, you can think about that as a double bond in a Lewis structure. Same thing. The carbon-hydrogen bond order would be 1 because it's a single bond. If you had a triple bond, it would be bond order 3, etc., etc.